Can you guys hear me and see the screen?
Yes.
Okay, thank you. While we're waiting for the others, if anybody has questions, they can chime in. Good morning. I'm going to start off by quickly reviewing what we discussed last time about the current voltage characteristics of a MOSFET. That's one of the most important portions of this course. And I want you guys to study this very thoroughly because I will test you on that in the exams, okay? And it won't be simple plug and play. You really have to understand the physics. All right, so what we said last time was you can think of a MOSFET as a gate voltage controlled resistor in the inversion region connecting the source and the drain, illustrated over here for a N-channel MOSFET. And to determine the IV characteristics, we first looked at a regular resistor, just an ohmic resistor, where we know, of course, that the current, I write that as ID equals the voltage applied, which I call VD, divided by the resistance. R, resistance is equal to the resistivity rho times the length of the resistor divided by the cross section, which is the width Z times the thickness of the resistor Y, which I bring into the numerator. Now, 1 over rho, resistivity, is the same as conductivity, Q mu N. So that appears in the numerator. And then I regroup terms as shown, so that VD over L is the constant electric field along the resistor, times the mobility gives you the drift velocity, as long as I'm in the ohmic regime, as shown over here. So this will be true for very high voltages, in which case the velocity would saturate, times the stuff in the parentheses, notice as units of charge per unit area. If I look at the resistor from the top, why is that? Well, N has units of number of carriers per unit volume, times the thickness of the resistor Y will have units of number per centimeter square. So that's how many carriers I see per unit area, looking at it from the top. And times Q gives you coulombs per centimeter square. So you can think of this as sheet charge, okay? Because we'll make the correspondence with the MOSFET in just a second. So the current per unit width in a resistor can be written as a sheet charge times the velocity of the carriers in the resistor, which kind of makes sense. And then if the width of the resistor is Z, you simply multiply by the width. Now, sometimes the width is indicated as W in the literature. We chose to use Z because we have chosen this as a Z-axis, and we reserved W for depletion width, so we didn't want any confusion. But having said that, many papers and books will use W instead of Z, and they'll interchangeably use CI, which is the gate insulator capacitance. CI equal to insulator capacitance divided by the thickness of the insulator, or Cox, which is epsilon oxide divided by the thickness of the oxide, because in most cases, the insulator happens to be an oxide, okay? All right, so now that I have that expression for the resistor, then we looked at the MOSFET and try to make the correspondence. So we need to have some way of coming up with an expression for the sheet charge per unit area in the inversion region, okay? To do that, we looked at the capacitance voltage behavior. So this is the gate overall capacitance C as a function of the gate voltage. And we see, of course, if it's an P-type substrate, so it's P silicon, because I'm looking at N MOSFETs. For negative gate voltages, the holes are attracted to the surface, so I have an accumulation layer, and therefore I have a MOS capacitance equal to CI or Cox. But then as I make my gate voltage more and more positive, I start pushing away the majority carrier holes. I start forming a depletion region in series with the oxide capacitance, and therefore the overall capacitance keeps dropping until you reach the maximum depletion width corresponding to a band bending of 2 phi f, twice the Fermi potential. Phi f is the difference between the mid-gap level and the Fermi level, and is therefore a measure of the doping level in the semiconductor. Okay, so phi f equals kT over q log of hole concentration, which is Na divided by Ni, the intrinsic carrier concentration. Okay, so if the bands bend by phi f, we saw that the intrinsic level meets the Fermi level, but then to get strong inversion, it has to bend by phi f, so that the surface is now as strongly N-type as it was P-type, okay? And that, of course, is my definition for strong inversion. And that voltage is what I call VT, which is this term in the parenthesis over here, okay? So we got the expression for the threshold voltage by adding the gate voltage that's dropped across the oxide, which is this term over here, the depletion charge per unit area. Sorry, the depletion charge by unit volume divided by CI. So that's the voltage drop across the oxide. And then the voltage drop across the semiconductor is phi s, the surface potential, which at threshold is equal to 2 phi f, measured with respect to the flat band condition. Okay, so the first two terms give you the voltage drop across the semiconductor, and the third term gives you the voltage drop across the gate insulator. Okay, so that's my VT. So once I recognize that, then I can look at the CV characteristics, and I see that the VT corresponds to not quite the minimum, it's slightly above the minimum for reasons that we haven't really discussed. But the important point is, once the gate voltage exceeds VT, we saw that the capacitance goes up very, very steeply, much more steeply than the way the capacitance goes down as the depletion region is expanding. So you can kind of approximate this part in the inversion region almost like a vertical line. And then it maxes out at Cox or Ci once again, because now I get a sheet charge of inversion electrons at the surface, okay? So if that's the case, then if I've applied a gate voltage of Vg, and I want to figure out how many inversion charges I have per unit area, you make use of the fact that the capacitance C is defined as, in this case, not just charge over voltage, but dq over dV. And obviously, you can then invert that, you can integrate. So then the charge becomes integral of C, that's overall MOS capacitance, which is a voltage dependent capacitor, as you can see, dV, right? To get the inversion charge, below VT, there's hardly any inversion charges. So you basically have to integrate from VT to whatever the gate voltage is, okay? So the limits of integration will be VT to the gate voltage, okay? Now this integral, of course, is nothing but the area under this curve, right? Which I'm showing by the shaded region. And you can approximately write that as the height of this rectangle, which is Cox or Ci, times the base of the rectangle, which is Vg minus Vt. And that's what I have over here for the inversion charge. Okay, so it's the height of the rectangle Ci or Cox, and the base is Vg minus Vt. The Vt is the term in the parenthesis. Okay. Now, that's of course if the drain voltage was grounded. All right, so that I have a uniform inversion region throughout. So the additional complication in the case of a MOSFET, or as you saw earlier for a JFET or a MESFET, is the fact that as the drain voltage is gradually increased, the current flows from the grounded source towards the drain, and the channel potential will rise from 0 near the grounded source all the way up to VD because of the drain current flowing. Okay, and that potential variation won't be a linear variation like in a regular resistor, but it'll have to curve up, meaning that the electric field along the channel will increase from the source end to the drain end. How do I know that? The electric field is equal to minus dB dx, and the slope is gradually increasing. Okay. Why does the electric field have to increase? Well, what happens is as the drain voltage increases, I have different Vx's along the channel. This is my x-axis. So the voltage difference between the gate and the channel at different points will change, right? Because at the source end, it'll be Vg minus V source, which is grounded, so that's Vg. At the drain end, it'll be Vg minus Vd, and at some intermediate point, it'll be Vg minus whatever the Vx is. Okay, so what I have to do is, wherever I had the surface potential, which was the 2 phi f plus flat band, you have to add the voltage drop due to the drain current flowing to that. So that's what I've done over here. Similarly, the depletion charge, if you look back at your notes, was in terms of 2 phi f before, but now you have to add 2 phi f plus the voltage drop Vx along the channel. So that's additional complication. Okay, and the upshot of that, as you saw, was the cross-sectional area of this induced resistor, this inversion region, gradually reduces from the source end to the drain end because Vx is rising. All right, and it's because of that, and because you have to have the same current flowing across every cross-section, the electric field along the channel has to rise, so that the product of the electric field times the cap concentration times the reduced cross-section all balances out so that you get the same drain current everywhere. And it's the same physics that we discussed for other transistors, such as the JFET or the MESFET, qualitatively last week. Okay?
The capacitance curve you're using versus voltage is for low frequency. So if at high frequency, would you do a similar analysis with the
I'll talk about high frequency effects today at the end of the lecture. Okay, yeah, you're right. So far, it's all DC or low frequency. Yeah, high frequency effects are very important, and I'll touch upon that at the end of the lecture today. Very good. Okay, all right. So once I have this form for the inversion charge as a function of position x, where the voltage drop is Vx, you can then use that to come up with an expression for the current. It's basically a drift current. ID can be written as the charge, Qn per unit area, times electric field, which is dVx divided by dx. But here I have brought the dx over to the left-hand side because I'm going to do an integral. And then I integrate on the left-hand side with respect to x between the source, which is 0, to L, which is the length of the channel. Now, since ID is constant, that just works out to ID times L. On the right-hand side, I integrate between 0, which is the source voltage, to Vd, okay? And I have this complicated function over here. Now, at that point, we made initially a simplifying assumption. We said that, okay, let's initially assume that the drain voltage is small. That puts us in the so-called linear region. So if my Vd is small compared to 2 phi f, you can kind of ignore momentarily the Vx term over here without incurring much of an error. But you still have to retain the Vx term over here because that's a linear term, okay? So with that, you simplify the expression that you have to integrate for the charge as this. And if you integrate that, the first two terms are independent of Vx. So that simply gives you this term over here, okay? It'll give you Vd. So that'll be Vg minus Vt, integrating between 0 and Vd, that gives you Vd. That's the first term. The second term is the integral of Vx dVx. That'll be Vx squared over 2. So that gives you this final term over here, okay? Now this only works as long as the drain voltage is small compared to the VG minus VT, and that's of course the so-called linear region, where the current increases more or less linearly with drain voltage. So it's like a resistor. But of course, we saw that as the drain voltage is increased, the channel gets gradually pinched off. So this part has a higher resistance than over here, and the curve starts bending over, and ultimately at VD sat equal to VG minus VT, the channel gets pinched off, and beyond that point, at least for this first order analysis, the current will not increase any further. It will saturate at what's called ID saturation, okay? And you can come up with an expression for that ID sat by taking this linear region expression, and I simply plug in VD sat, which is equal to VG minus VT, and you'll see that you end up getting VG minus VT whole square minus half VG minus VT whole square. So that just works out to this term divided by half VG minus VT whole square, meaning that the curves, the drain current does not depend on drain voltage, and it depends quadratically on VG minus VT square, okay? So the spacing is going to be gradually increasing. This is all for the simple first order analysis applicable for long channel devices. We'll see the important changes for short channel today, okay? So these are known as output characteristics because I'm plotting output current as a function of the output voltage for different input voltages. Now, we also mentioned in passing that you don't need to make this approximation of ignoring the Vx in this term over here, which is this depletion charge, okay? So then I'm taking into account the variation of the depletion charge with position. So you have to integrate the square root term. So it's not complicated, but the expression looks a little bit messy. Since I'm integrating the square root term for the depletion charge, you end up getting, if you integrate square root of x, you get x to the power 3/2. So you get these 3/2 terms over here, okay? So this is a much more accurate expression. And interestingly, you can go back from this accurate expression back to the simple expression for low drain voltages by doing a Taylor expansion for small values of VD. And not surprisingly, you're back to the simplified expression that we did the other way by ignoring Vx over here, okay? In this class, I'll only ask you to use the simplified versions over here for the IV characteristics, okay? In a graduate class, you look at the more elaborate expression. But in this class for homework and exams, I'll just ask you to use the simple expression, okay? Now, once you get the expression for the current voltage characteristics as a function of drain and gate voltage, you can come up with circuit parameters such as conductance, which is change of output current over output voltage, or things called transconductance. This is some sort of gain because now I'm looking at change of output current as a function of change of input voltage. It's kind of a funny kind of a gain, okay? Not voltage or current gain, but it's called transconductance. All right, so that was for NMOS. PMOS, we saw that the polarities of the voltages are negative, okay? And then you can combine both of them. They work hand in hand in what's called complementary MOS that we'll discuss actually next week when you talk about process integration, all right? We also looked at what are called the transfer characteristics of the transistor. So the previous set of curves were called output characteristics, because I'm looking at output current as a function of output voltage. But you can also look at transfer characteristics where I look at output drain current as a function of input gate voltage, okay? So if I replot the characteristics this way, say for low drain voltages where I initially ignored the quadratic VD squared term, you get a linear curve because it only depends linearly on VG, okay? And then you can see that if I extrapolate this ID curve to 0, it should intersect at VG equal to VT, okay? So we saw that was a way of calculating experimentally what the threshold voltage is, and you can do that both in the linear region or in the saturation region. Of course, in the saturation region, because of the quadratic dependence of current on gate voltage minus VT squared, you have to take the square root of that, okay? Now, what we'll see today is this measurement in the saturation region will actually give you a lower value than in the linear region for reasons to be discussed in a second, all right? The other thing that we talked about was this channel mobility. This mobility is called the effective channel mobility, okay? And tends to be lowered, much lower than in the bulk semiconductor because you have an additional source of scattering called surface roughness scattering. And that's due to the fact that this interface between the insulator and the semiconductor is not going to be a perfect interface. You'll have atomistic scale roughness, and anything that is a deviation from perfect periodicity causes scattering of the carriers, okay? Now, that mobility actually also drops as the gate voltage increases and this transverse electric field increases. And the analogy that we used was, it's as if I take this inversion carriers and I move it across a piece of sandpaper, okay, which is this rough interface, okay? And more tightly, I press this electron gas against the sandpaper, the frictional forces will be more pronounced, right? And that's why the mobility drops as I pull it closer to the interface for increasing electric field, okay? And interestingly enough, that mobility versus effective electric field curve turns out to be a universal curve, which, as I said, wasn't expected, but it was a major discovery in the late 1970s. All right, now, where we left off last time, any questions, by the way? Like I said, I repeated this part because it's so important, so fundamental, and I want you to study this every which way you can so that you get this part very well, okay? Some of the more
Banerjee?
Yes.
I do have a question. For the drain voltage across the channel, why is it increasing like quasi-exponentially, like not linearly?
Right, it's not exponential, but
right.
It's increasing. You're talking about this curve. Let's see, you're talking about this curve over here, right?
Yes.
Yeah,
yes.
It's not an exponential increase, but it's a nonlinear variation where the
right.
slope along the channel, this is the electric field along the channel, clearly increases, right? Because electric field is minus dV dx, and the slope near the source end, you can see, is less than the source at the drain end, right? And the question is why, right? That's your question, right? Why is it not a linear variation, right?
Yes. Yeah.
Yes. So if it is a linear variation, what would the slope be? It's constant throughout, right? That means that the electric field along the channel is constant throughout, right?
Yes.
Now, if that was the case, and because I have a thicker inversion region over here, it's as if the cross-section of the resistor is thicker near the source end, and the cross-section of the resistor is thinner near the drain end, right?
Yeah.
And have the same electric field, what's going to happen? I cannot satisfy current continuity, right? But I have to have the same current flowing across every cross-section. So as my effective thickness of the resistor shrinks, the electric field has to increase by exactly the same amount, if you will, okay? So that the product stays the same throughout.
Okay. Makes sense.
And the same physics as for the JFET or the Mosfet that we mentioned a couple of lectures back. Very good question. Okay. Now, if you look at this transfer characteristics, the first order model seems to predict that as soon as the gate voltage is reduced to VT, the threshold voltage, the current should go abruptly to zero, right? But in practice, what one finds, the current doesn't go abruptly to zero, it goes down gradually to zero. And this current below the threshold voltage is known as sub-threshold conduction, all right? And that turns out to be a very important parameter for a transistor because it's a hallmark of how good the transistor would act as a digital switch. Because clearly, what's a good switch? A good switch is if you turn it on, you should turn on full blast. And the moment you turn off the switch, you'd hope that the current goes down abruptly, right? But it doesn't. When I turn on and off the switch, it doesn't go up 100% and it doesn't go down 100%, right? Which is kind of unfortunate, right? I mean, you like a digital switch to be perfectly on and off, but the physics dictates that it goes down exponentially with gate voltage. And that's what I was showing at the end of the last lecture, okay? So here, I'm looking at the transfer characteristics once again, which is the output drain current as a function of the gate voltage, but on a semi-log plot. So now I'm looking at log of the current. So notice this is a log scale on the vertical scale as a function of linear gate voltage, while the previous curve was a linear plot. So this was a linear drain current as a function of linear gate voltage. But now I'm taking log of the current as a function of gate voltage and focusing on this region, okay? And as I said, in a perfect digital switch, you'd hope that this curve would be a vertical line, right? So that as soon as you go below threshold, it turns off abruptly, but it doesn't. What we find is it looks like a straight line on a log linear plot, which obviously means that the drain current decreases exponentially with gate voltage, okay? And that's what I'm showing in this curve over here, which I'm not going to go into the analysis of. Okay, it's a little bit complicated. We discussed this in a graduate course, but basically what you have to do is below inversion in the channel, you don't have below threshold, you don't have strong inversion. You have what is called weak inversion. Okay, so that's a region of band bending less than 2 phi f. Okay, so under those conditions, you end up having a little bit more electrons over here and fewer electrons near the drain end. And of course, anytime you have a concentration gradient, what kind of current flow does that give rise to? Anyone? If I have more electrons here than over here, concentration gradients lead to diffusion currents. Okay, so you now, under these conditions, below threshold you get diffusion currents, while above threshold we saw that you can do the analysis based on drift current in this resistor. All right, and by doing that analysis you get this. Now, the thing that I do want to point out, however, is you can kind of understand the overall behavior by looking at an equivalent capacitor circuit of the structure. Okay, and that's what's shown over here. What I find is in the gate oxide region, that acts like a capacitor, Ci or Cox, equal to epsilon I over the thickness of the oxide, or epsilon ox over the thickness of the oxide. This is all per unit area, of course, in series with the depletion capacitance, right? Where the depletion width, of course, is a function of voltage. So that's what gave rise to the CD, which is now equal to epsilon, not oxide, but epsilon of the silicon or semiconductor divided by the depletion rate, which is voltage dependent. So the CD is voltage dependent. And that's why, of course, the CV characteristics behave like that, right? C as a function of voltage, that's Ci, then it goes down, and then, in inversion, it becomes Ci again. So I'm looking at this part over here, all right? Now, in addition to this capacitance, it turns out you also have what's called a fast interface state capacitance. I don't know if you recall that. We said that at this interface, you'll always have some defects, structural defects, and those will give rise to energy states in the band gap. So that's my EC, EV. And when the bands bend, these interface states sometimes will move below the Fermi level, in which case they'll be occupied by electrons. And then when the bands unbend, the same states, if they move above the Fermi level, will not be occupied by electrons. Okay, anything that results in some sort of charge storage is tantamount to capacitance, and that's what this capacitance is. Okay, it's called the interface state capacitance, which you can see if you look at the structure is in parallel with this. Okay, so once I have this equivalent circuit, let's see what the impact of a gate voltage would be. So I'm applying a gate voltage over here, which is at this node, okay? And I want to see how the drain current changes as a function of this gate voltage. Well, if you stop to think about it, the channel doesn't really care about what the gate voltage is. The channel cares about what the voltage at the surface of the semiconductor is, right? And for that, remember, we drew the band diagram, and we said that in the source, we have the conduction band close to the Fermi level. In the channel, you have the valence band close to the Fermi level, and then in the drain, you do this. Remember that picture? Okay. So really, you care about this potential because it's only when you reduce this barrier between the source and the channel can you get conduction, right? So what you have to do is you have to look at this equivalent circuit, and as we change this gate voltage, you have to figure out what the potential is at this node. This corresponds to the surface of the semiconductor. Okay, so this is something that you can do on your own. You know, look at your circuits class and see what the voltage division would be, keeping in mind the impedance of a capacitor varies as what? It varies as 1 over j omega c. Omega is the frequency. Okay, here of course we're looking at DC, so it's basically proportional to 1 over c. Okay. So you do the voltage divider based on 1 over Cox or Ci, and this is 1 over CD plus Ci because these are in series. And that equivalent capacitance ratio will give you this term over here. Okay, I'm not going to go through the algebra, it's trivial. I want you to do that on your own at your leisure. Okay, so the important point is you look at this exponential dependency of the current, drain current, on the gate voltage. Okay, and take into account this voltage division because of these capacitors, And that allows you to define what's called the sub-threshold slope, which is given by this, okay? Now, although I call it sub-threshold slope, I really should have called it inverse slope, because the units of this are millivolts per decade, as shown over here. What does that mean? That means that in this particular case, for example, I'm getting a measurement of 70 millivolts per decade. That means I have to change the input gate voltage by 70 millivolts to change the drain current by 1 decade, by a factor of 10. Okay, so it's not really the slope, if you think about it, it's the reciprocal of the slope, okay? But people are kind of sloppy, and people conventionally call it the subthreshold slope, okay? So if I get a steeper curve, the slope is actually higher, right? But the value of the subthreshold slope drops. Okay, so the smaller the slope, the smaller this number, the better, because that means a steeper slope. You guys with me? All right. So it turns out this first prefactor, that's natural log of 10, that's roughly 2.3, times KT over Q, which at room temperature is 26 millivolt, and that works out to 60 millivolts per decade. And the rest of it is a capacitor divider. So the question then becomes, what is the theoretical minimum of the subthreshold slope of a MOSFET? Well, to make this whole thing smallest, the best that I can do is to make this term 0, right? Which means a high value of Cox or a low value of this numerator, right? But even if I did that, I'm still stuck with 60 millivolts per decade. What it means is the best theoretical value of the subthreshold slope, the best you can possibly do, is 60 millivolts per decade. You can't do any better than that. And the question, of course, is why? Well, that turns out to be ultimately because of the Maxwell-Boltzmann distribution. Okay, so basically what happens is, if you look at this band diagram, we know that the carrier concentration, you have more carriers at lower energy, and as you go up to higher and higher energy, you have fewer and fewer carriers, which basically scale as e to the power minus energy over KT. That's your Maxwell-Boltzmann classical limit of your Fermi-Dirac distribution function. So these high energy carriers can go over this barrier, even in the off state, okay? And the way you can modulate the leakage will give you the subthreshold slope, okay? So people sometimes jokingly will call it the tyranny of Boltzmann, okay? To make the transistor perform as better and better, the best that you can do is to make your oxide capacitance as large as possible, which means you make the oxide thickness as thin as possible, okay? Which kind of makes sense, which means that the gate has very good control over the channel potential. But as I make my oxide thickness thinner and thinner, what technological problem did you face? Anyone?
Tunneling?
Very good. Tunneling leakage current, okay? And that's why people went to high K dielectrics. So you don't make the oxide of the high K much thinner, but instead you increase the dielectric constant of the dielectric. And hafnium oxide is the current champion. Now this limit, of course, is only at room temperature. If you reduce the operating temperature of your chips, your slope would be steeper, right? And there's some applications where people will operate chips at liquid nitrogen temperatures. That's called cryogenic CMOS, okay? But of course, you can't do that for, you can't dunk your iPad into a liquid nitrogen bath, but people working on supercomputers, they can afford to play tricks like that, okay? The other thing that's important technologically is you want as good of an interface to minimize the CIT, right? So you want as low of a defect density at this interface as possible, okay? I'm going to skip the next one. This is a phenomenon called gate-induced braid leakage. You can read up on your own if you want. It's more of a complicated thing due to band-to-band tunneling in the semiconductor itself, okay? All right. So now I'm going to spend the rest of the lecture talking about what are called short channel transistors. So far we've been looking at long channel devices, where this is the starting formula that you have to use for your exams or homework problems, okay? And from that, you can then get the saturation drain current. So this applies in the linear region. So if I draw a dotted line, sorry, a smooth line, okay? So that's my VD SAT curve. So the left-hand side of this is the linear region. The right-hand side is the saturation region. Here, by the way, I'm showing both N MOSFETs, and on the left-hand side, I'm superimposing P MOSFETs. Okay, so here you see that the voltages are negative, gate voltages are negative. For the N MOSFETs, all the drain voltages and gate voltages are positive. I'm showing both of them side by side to make a point. Okay. Just a second. All right, so let's look at these N MOSFETs that we have derived. Once again, word of caution, although in our textbook we call the width of the transistor Z, in the literature very often people will call the width W, and similarly COX is the same as CI, because most often the insulators happen to be oxides, either silicon dioxide in the past or things like hafnium oxide these days. The mobility over here is not the regular bulk mobility, but it's the channel mobility, which is lower than the bulk mobility. Now, how do I decide whether I'm in this region or this region? So that's one typical gotcha, okay? So if I gave you, for example, VG of say 5 volts and had a threshold voltage of 1 volt, and the drain voltage was say 0.1 volt, okay? What you have to see is my VD greater than or less than VG minus VT, because VG minus VT is my VD sat. Okay, so let's say VD was 1 volt. Okay, is that in the linear or the saturation region? Well, VG I've said is 5 volts, and VT says 1 volt. So VG minus VT is 4 volts. So if I apply a drain voltage of 1 volt, that's clearly less than VD sat, means I'm in this region, right? In which case I have to use this curve. On the other hand, if I raise the VD to say 5 volts, okay, what's going to happen? That is now greater than VG minus VT of 4 volts, right? So in that case, if I plug in 5 volts for the VD, I'll get the wrong answer. Instead, what I have to do is I have to plug in VD sat, because I'm on the right-hand side of this curve, okay? So if I do that, so instead of this, I have to use VD sat square over 2 or VG minus VT square over 2, okay? So that's really a common error. So in the exam or homework, make sure that you know which region I'm operating in, okay? If you choose the wrong expression, I'll penalize you in the exam, all right? Now, all that I've discussed is true for long channel devices. For short channel MOSFETs, where the channel length between the source and the drain is small, one finds that you end up getting a slightly different expression for the IV characteristics, okay? What you see is the ID in the saturation region does not depend on VG minus VT squared over 2, as I've derived before, but rather has a linear dependency, more like VG minus VT times my saturation drift velocity. Why is that? It's very easy to derive that. You see that this term, CI times VG minus VT, what is that? That's nothing but your inversion charge per unit area, right? You see, if we go back a couple of slides. That's what I derived for the long channel, right? So VG minus VT times CI or COX is this rectangle, right? That's the area under the curve. That's my inversion charge per unit area. Now I'm looking at a long channel, short channel device. If it's a short channel device, what do you expect will be the electric field along the channel? It'd be VD minus VS, which is 0, roughly divided by the channel length, right? Of course, it's not a linear variation of the potential, but roughly speaking, order of magnitude, it'd be VD divided with the channel length. And if channel length is very, very short, I'll be in the high field region. The carriers travel at V sat, okay? So the way you can kind of derive the expression for the current in a short channel MOSFET is you say that, okay, the sheet charge is given by CI VG minus VT, and all these carriers along the channel throughout travel at V sat. This is an approximate analysis, okay? And then that's per unit width. If the width of the transistor is Z, you simply multiply by Z, okay? This is an approximate analysis. It's not 100% accurate, but it'll be good enough for our purpose, okay? So CI times VG minus VT is my inversion charge. The carriers are traveling at saturation velocity because now my electric field Vd divided by the channel length is in the saturation region of the drift velocity. That's the current per unit area. Then get the total current multiplied by the width of the transistor. Okay. Now the good thing from a circuit design point of view is now in the output region, hopefully I get a high output impedance, in which case the drain current should have been flat, and I get a linear dependency of the output current with input voltage. Okay, so I get linearity of gain and stuff like that. But let's go back to this output impedance business. So in the long channel devices, remember the curves were flat, which means that the output impedance was close to infinity, right? Because the impedance is given by del VD, del ID, right? So if the curves are flat, the del VD was non-zero, but the del ID was zero, in which case the output impedance would be very, very high, which is good, right? Unfortunately, however, in a practical short channel transistor, you see that the curves slope upwards. So what's going to happen to the output impedance? Is it going to be lowered or will it stay at infinity?
It'll be lowered.
Lowered. Is that a good thing? No, it's not a good thing. You would like the output impedance to be infinity, okay? You'd also want the input impedance to be infinity, which, you know, it works because you have an insulator, except if you have a very thin insulator, you get this, you know, pesky business of tunneling, okay? So those are the technological challenges that you face in a short channel device. And we'll see in a second why the curves don't saturate, why they bend upwards in a short channel device. There's some physics behind that, okay? The other thing that I see by looking at these curves, these are, by the way, actual experimental data for a 3 nanometer gate oxide and 0.1 micron channel length. This is experimental data from my days at Texas Instruments. What is the other thing that you notice? So notice that the voltages are comparable, okay, except for positive and negative. What's the other thing that you notice when you compare the PMOS versus the NMOS? PMOS currents are lower, right, for comparable voltages. What do you think that is?
Lower hole mobility.
Sorry?
Lower hole mobility.
Very good. So the channel mobility of holes is roughly a factor of 2 lower than for electron mobility. Okay, this is with surface roughness scattering and all that. Okay, that turns out to be a problem from a circuit layout point of view, because in CMOS, as I mentioned, you typically will have both N channel and P channels always work hand in hand. It'd be nice to have them have comparable drive currents. Because they don't, you're sort of generally forced to make the width of the P channel devices roughly twice the width of the N channel devices, okay? To kind of compensate for the lower hole mobility. Now, what is a double whammy is the fact that if I look at the source drains, in the PMOS, you have to dope it with acceptors, okay, while in NMOS with donors. It turns out the acceptors, which are boron in silicon, unfortunately, you can't put in as many boron in silicon as you can acceptors like arsenic and phosphorus. So as a result, the source drain series resistance that I think I mentioned last time also is higher for PMOS, okay? So not only is the hole mobility lower, you end up getting a higher source drain parasitic resistance in the PMOS, and both of those cause the drain current of the PMOS to be lower than for NMOS, which in turn then forces you to lay out the width of the P channel to be twice, not necessarily the width, yeah, the width of the P channel to be roughly double that of the N channel devices. I mean, that's what people do, but it kind of makes the layout of the circuits a little bit more messy, okay? Okay, so let's say a little bit more about this saturation, this IV characteristics of the short channel devices, okay? So for short channel devices, by the way, what is short channel, okay? From a technology point of view, people have found that when you shrink channel lengths from, say, 10 micron channel lengths, which were in vogue in the 70s or 80s, I forget the exact time period. Okay, you can look at this Moore's law curves that we have in chapter 9 of the textbook. So those are definitely long channel. By the time people went to about half micron or so, people started seeing these short channel effects that I'll be talking about next. And you start getting this sort of a dependency, okay? And that lasted till about, say, 1/10 of a micron. Now, once people started going below that, these days the channel lengths are much shorter than that. They're down to as short as, 7 nanometers, okay? Or let's say 10 nanometers, okay? So roughly 0.1 micron is 100 nanometers. So 10 nanometers is a factor of 10 smaller than that even, okay? And that's where we are currently for state-of-the-art chips made by, say, Intel or Samsung or all these companies, okay? Now, for such short channel devices, the physics has changed even more, okay? And that's the subject of this slide. So people now see that the current in the transistor is actually limited by the rate at which you can supply carriers from the source into the channel, okay? What I'm looking at this figure is the band diagram between the source and the drain, okay? So that's kind of band diagram that we have drawn before, okay? Suppose it was N plus source drains. Remember we said that, okay, you have this sort of a band diagram, okay? Here I'm looking at it now, but now for increasing drain voltages, well, if the drain voltages go up, what's going to happen? The electron energies will keep reducing, right? That's what I'm showing in these figures, okay? So I have a high drain voltage, the source is grounded, and depending on the gate voltage, which I can show on this diagram, you can lower this energy barrier between the source and the channel, right? Now, obviously, what you'd want in a good transistor is it is a gate which should control the source to channel barrier, right? Not the drain. But in a short channel device, we'll see in the next couple of slides, unfortunately, that's what happens. That's an effect known as drain-induced barrier lowering, which is responsible for this lowering of the output impedance, okay? But here, I want to talk about something else, and that is, in a short channel device, what I've claimed is that I have a high electric field along the channel, which is roughly equal to VD divided by L, and we said that the carriers travel at the saturation drift velocity, more or less throughout the channel, right? And that's why you end up getting this characteristic, right? So we said that the carriers travel at the saturation drift velocity, more or less throughout the channel, and that's my inversion charge. So charge times velocity gives you the current per unit width, and then multiplied by the width of the transistor, right? What's been discovered over the last decade or so is once you go down to super short channel lengths, say 10 nanometers, or these days 7, and I believe industry is moving towards 5 or 3 even, okay, in R&D labs, the story has changed, and there's another twist and turn. And now you're in a regime where you're source injection limited current. What the term means is I'm no longer limited by the saturation drift velocity of the carriers in the pinch-off region in the channel, okay, which is this region, but rather I'm limited, the current's limited by how quickly you can supply carriers from the source into the channel, okay? So it's not limited by the electric field and the saturation drift velocity, mostly in the pinch-off region, but it's now limited by source injection across this source to channel barrier. So that's the latest evolution of the story of transistors. And this physics was developed at Purdue by Dr. Mark Landstrom. And actually, prior to that, it was discovered in Japan by a guy called Natori. Okay, so it's known as the Natori-Landstrom theory. Okay, so for state-of-the-art nanoscale MOSFETs, the drain current is limited by how quickly you can supply carriers from the source to the channel, okay? Not the saturation drift velocity over here. Now, the physics of this is very, very interesting. And under these conditions, you have to use not drift diffusion type transport. You have to use full-blown quantum mechanics. It's called quantum transport, which obviously we can get into. You can kind of think of these electrons as electron waves propagating in some sort of a waveguide made up by the channel. Physics is absolutely fascinating. So hopefully, if you're interested in the field, you'll take graduate courses dot at UT. All right. Now, these quantum mechanical effects are very, very key to understanding how modern nanoscale MOSFETs work, okay? Which, once again, unfortunately, we don't have the time to get into. These are all subjects of a graduate program, but I wanted to give you a preview, okay? First of all, there's electrostatic effect, okay? And that's what's shown in the lower figures over here. What am I seeing? Over here, I have an isometric view of a planar traditional bulk MOSFET, bulk meaning made in bulk silicon, okay? So what you have is you have the source, the drain, and then the gate, which is this green rectangle, which controls the current flow from the source to the drain through an inversion region that would lie underneath the gate. Okay? The gate, of course, is separated from the channel region shown in gray. So the gray region is the semiconductor. So it's the green electrode is separated from the channel region by a very, very thin gate dielectric made up of a high K dielectric. Okay. The other thing that you see is surrounding this transistor, which has a length equal to that dimension. So that's my length of the transistor. That is the width of the transistor. Okay. But surrounding this transistor, I have what's called a field oxide. So that's an isolation or field oxide. Okay. And this actually surrounds the transistor on this side also. So it surrounds it on all four sides. Okay. And that's what makes this transistor not leak current to maybe another transistor, which might be located over here, or another transistor over here, another transistor over here, and all that. Okay. How does the thick oxide guarantee isolation? Well, remember the oxide capacitance, Ci, equals epsilon insulator divided by the thickness of the insulator, D or Tox, right? Then the high K dielectric, I have a very thin Tox, and therefore I'll have a large value of Ci. Now, if I have a large value of Ci, the Vt, which depends on flat band voltage plus 2 phi f minus Qd by Ci. Qd has a negative sign in the case of NMOS, so this is plus. So if Ci is very, very large, Vt would be small, right? And in a modern transistor, you typically have VTs of around 0.6, 0.7 volts. Well, I forgot to mention that. Let me go back for a second. So in modern transistors, the threshold voltage is designed to be around 0.6, 0.7 volts. And that's really determined by this subthreshold slope of 60 millivolts per decade, okay? Why is that? Well, if my VT is say 0.6 volts, where the transistor is turned on, if I go down to 0 volts, that means I'm having, so assume that I have 60 millivolts per decade, the ideal case, right? So from a VT of 0.6 volts, every time I go down by 60 millivolts, hopefully the current goes down by a factor of 10, right? So that by the time I go down to 0 volts, I should be down in current by roughly 10 orders of magnitude, okay? You don't get 10 orders. In a good transistor, you get about 7 orders of magnitude between the on current and the off current at 0 gate voltage, okay? So that's the reason why you don't want threshold voltages to be much less than 0.6 volts or so, okay? Because suppose I made a VT of say 0.2 volts, what's going to happen? Even when the gate voltage is 0, I'll have a lot of subthreshold leakage, right? And on top of that, when I have statistical variations of threshold in manufacturing, I get a large variation of the leakage current in the MOSFET, okay? So you're stuck to VTs of around 0.6 volts or so, okay? Which in turn limits how much current you can get out of the transistor. So if I have a 2.5 volt VDD, the maximum current that I get will be proportional to VG minus VT, or 2.5 volts minus 0.6 volts, right? So that's kind of what limits how much you can lower the operating voltages of a transistor. All right, so going back to this figure over here, the reason you get electrical isolation is here, you see that the oxide thickness is very, very large, meaning that the capacitance of a parasitic transistor in this part would be very, very low, the gate capacitance. In other words, the VT would be very, very large. So the VT over here may be 20 volts, while the VT over here is 0.6 volts, okay? That's how, if I have a 5 volt power supply, for example, these parts of the semiconductor will never turn on, right? And that's how you guarantee electrical isolation of this transistor from neighboring transistors. Very, very important, because remember, you'll have literally billions of these transistors crammed into a piece of silicon, maybe a centimeter by a centimeter, okay? Now, the other thing is you'd like this current to be controlled by the gate, not by the drain directly, right? So that leads us to a variety of short channel effects. I'm going to come back to this after I talk about the short channel behavior. I think it'll make more sense then. All right, so what are these short channel effects that I talk about, which limit what's called the scaling of the transistor? The term scaling means as I go from one generation to the other in accordance with Moore's law. So this is the year of the technology. And if this is my channel length, one finds that the channel lengths have been shrinking as a function of time. Okay, this is typically shown on a log scale. And these curves you may have seen in the literature are examples of what are called Moore's law. Moore is Gordon Moore, who was founder of Intel Corporation. Okay, so he made an observation back in the 60s, in fact, that roughly every 3 years, these transistor dimensions shrink by a factor of 2, roughly. Okay, and if I can shrink the transistor dimensions, if I now look at the number of transistors as a function of time, it goes up exponentially. Okay, it doubles roughly 3 years or so. Okay, so these exponential dependencies of reduction of feature size and increase of transistor count are examples of what are called Moore's law. Okay, and this is discussed in chapter 9 that you may want to read up on. The question, of course, is why do people want to reduce the channel length of a MOSFET? Okay, so that's this dimension. But clearly, one advantage is if you make the transistors smaller in size, you can cram more of them on a certain piece of silicon, and you can have a larger number of transistors on your IC, right? In a modern IC chip today, you'll have, like I said, billions of transistors in a piece of silicon, maybe 1 inch by 1 inch, okay? And that's what you have in your Pentium microprocessor chips in your laptop, for instance, okay? But it also turns out that if you make the transistors smaller in size, the performance of the transistor also improves, okay? For instance, Branch brought up this business of high frequency performance, right? Now let's see physically, what would you expect would happen to the high frequency behavior? Well, the carriers have to travel from the source to the drain, right? If I make my channel length shorter, would the transit time be shorter or longer? Obviously, it'll be shorter, right? And what do you think would happen to the frequency of performance then? It should go up, right? So you can cram in more transistors and the frequency of the devices could go up, okay? Now, people doing this business of scaling down the transistors are guided by a principle known as the Denard scaling laws. Denard was an electrical engineer working, a very famous guy at IBM Yorktown. He's actually a Texan. He got all his degrees at SMU in Dallas, one of the gods in our field. So he came up with a so-called set of scaling rules which dictate how you reduce the channel lengths of a transistor by a factor of, say, alpha. Okay, alpha maybe by a factor of 2 as an example. Okay, so I want to reduce my channel length L, say, from 2 microns to 1 micron by a factor of 2 as an example. Okay, so what Mr. Denard said, what Dr. Denard said, is you can't just scale down the horizontal channel length and leave everything else intact. You have to reduce all the dimensions in concert by the same factor. That's the essence of the Denard scaling law, okay? So what he said was, if I reduce the channel length by a factor of 2, I have to make my source drain junction depth lower by a factor of 2. I have to make my oxide thicknesses lower by a factor of 2. And that's kind of what I'm showing, okay? You can also afford to shrink the widths by a factor of 2 or alpha in general, okay? And if you do that, you have to reduce operating voltages by a factor of to, let's see, where is voltage? Yeah, okay. If you do that, you can kind of keep the internal electric fields more or less constant, right? So the electric field along the channel is roughly VD divided by L, right? The channel length. So if I reduce this by a factor of alpha, reduce this by a factor of alpha, roughly speaking, the electric field stays constant, right? If we reduce the gate voltage by a factor of alpha and the oxide thickness by a factor of alpha, the gate oxide fields stay more or less a constant, right? So this is what he meant by constant field scaling, okay? And he said that if you do that, you won't get into trouble. But if you don't follow my rules, all hell might break loose, okay? Unfortunately, circuit designers are a very stubborn bunch of folks, okay? And what has happened in practice is, as technologists have reduced channel lengths gradually from one generation to the other, the power supply voltages have not reduced continuously like so, okay? Instead, what happens is, for many generations in ICs, the power supply VDD was kept at, say, 5 volts, while channel length shrunk, okay? And as the channel length shrunk, the electric fields kept increasing until the problem got so bad that, even circuit designers say, okay, we'll give up. Say, okay, we'll let the power supplies to go down by, say, from 5 volts to 3.3, okay? It stayed at 3.3 volts for several generations. The problem of electric fields keep increasing, okay? Then it went down to 2.5 volts and so on and so forth, okay? So the message is, unfortunately, because of system constraints, the operating voltages don't shrink in concert with the technology. They shrink in a stepwise fashion, okay? And as a result, these internal electric fields keep building up from generation to generation, okay? These fields keep building up. So what's going to happen? Well, if the gate oxide fields keep building up, you have tunneling problems, as we mentioned, okay? If these electric fields keep increasing, when I inject a carrier from the source in the channel, they keep gaining kinetic energy from the electric field along the channel, okay? So basically what happens is, I inject a carrier from the source, say at this point, what is the kinetic energy of that electron? Well, if it's at the band edge, what is the kinetic energy? It's close to 0, right? But then as it goes into the channel, you see that the slope increases, electric field increases, it's keeping gaining on kinetic energy, right? And that can be seen by imagining the carrier travels like this. Of course, it don't really travel like that because it always has scattering in the channel. So you'll gain some kinetic energy, lose some kinetic energy by scattering, gain some, lose some, but it'll become a highly energetic electron, or a so-called hot electron, okay? And you'll get a kinetic energy depending on the difference between the location of the electron energy and the conduction band edge shown over here, right? Now, if the electrons gain enough kinetic energy, suppose this was my EC, my EV would parallel to that, what's going to happen? Well, if I have a highly energetic electron that can bump into one of these covalent bonds and it can excite electron hole pair, right? You create a hole and a secondary electron, right? The other thing that can happen is highly energetic electrons can be injected across this oxide barrier. So if I look in this direction, I'll have a potential energy barrier between the conduction band of silicon and the conduction band of oxide. These hot electrons can surmount the barrier, give rise to what are called hot electron problems, okay? So those are the kinds of things that I'm showing over here. So you can get electron hole pair generation by impact ionization. The holes will travel towards the substrate, while the electron, the primary electron and the secondary electron go to the drain. And as a result, the current will not saturate, but go up. So that's one reason for the reason for the increase of the drain current. Okay. There's a whole bunch of these other effects, bad effects that can happen. Okay. Carriers can be injected into the gate oxide, and some of them can be trapped as fixed oxide charges. That's an example of hot electron damage that I mentioned in the last lecture. Okay, I'll elaborate on that again. All right. So the main message, like I said, is as you scale down channel lengths, the vertical dimensions also have to be scaled. My junction depths have to become shallower and shallower. Oxide thicknesses have to be reduced. The operating voltages hopefully have to reduce also. It does so in a stepwise fashion because of system constraints. The depletion widths have to reduce by a factor of alpha. How do I do that? Well, the depletion region is given by the voltage drop equal to half Q doping in the semiconductor W squared over epsilon. Remember that famous formula for p-n junctions? So basically what it says is, for a certain voltage, if I want to reduce my depletion rate by a factor of alpha, what do I have to do? I have to increase the doping by a factor of alpha, right? Actually, alpha squared. So my doping concentration has to actually increase by alpha squared to make sure that the depletion rate reduces by a factor of alpha, okay? So you want a higher channel doping, all right? So that's what's done in a modern transistor. But as I said, because of the power supply voltage is not scaling to keep the electric fields constant, you can get these hot electron effects or other short channel effects. So the hot electron degradation is shown in this particular figure. So what I'm showing is these electrons are being injected from the source, traveling towards the drain. If you look at the band diagram, sorry, that's my source end, that's my drain end. These electrons are going in, they're getting hotter and hotter. So here I have hot electrons, okay? And if it gets hot enough, they can be injected into the oxide. Why? Well, if I take a cut like this and I draw the band diagram, in the oxide, I have a large energy band gap, while in the silicon, I have a lower band gap. So I'm flipping this by 90 degrees, right? So if I was to plot the band diagram corresponding to this, that would be my conduction bandage in the oxide. And then that's my conduction bandage in the silicon. So I'm flipping the figure by 90 degrees. That's my EC in the oxide. That's my EFM, the work function, the Fermi level in the metal. That's EC, EV in the oxide, EC, EV in the silicon. Are you guys with me? So I'm plotting the band diagram as a function of depth, but I'm flipping the diagram by 90 degrees. So this is the high band gap in the oxide. That's a lower band gap in the silicon, right? So then, as I inject electrons and they become hotter and hotter, they're basically moving up in energy in the silicon channel. And if they gain enough energy, they can be injected into the oxide. They can be injected into the oxide, where some of these electrons or holes can be trapped in the oxide because the mobility of carriers, remember we said, is very, very small in amorphous oxide dielectrics. The extent of the injection would depend on the delta EC for electron injection or delta EV for hole injection, okay? And it turns out if this oxide was SiO2, this delta EC was roughly 3 electron volts, while delta EV was 5 electron volts, okay? So which problem do you think is going to be more problematic? Hot electron damage or hot hole damage? Anybody? I guess the answer is right there. Hot electrons, right? Because the electrons don't have to gain quite as much energy to surmount the barrier. Holes have to gain more energy, okay? The second factor is, someone just said correctly earlier, that electron mobilities are higher than hole mobilities. So for the same electric field, electrons can heat up more easily than holes can, okay? So historically, for a long time, hot electron problem was worse than hot hole problem, okay? What is the impact of that? The impact is shown over here, but I'm looking at the ID versus VG. So these are these transfer characteristics, where we saw that if you extrapolate the curve, you can get a rough measure of the threshold voltage. So my threshold voltage is somewhere over here. So before operation and after device operation, that's what I'm calling electron stressing. Notice that the curves shift to the right, meaning that the VT has gone up. Why would the VT go up? Well, if I inject electrons and some of them get trapped over here, and I look at the threshold voltage expression, remember that is the flat band voltage, which is phi ms, the work function difference between the metal and the semiconductor, minus Qi over C ox or Ci. So these two terms gave me the flat band voltage, right? Now Qi was the charges in the dielectric, but the weighted sum, right? Charges close to this dielectric count more, charges close to that dielectric induce emit charges in the metal gate that don't cause band bending in the semiconductor, right? So you have to do the integral of charge distribution weighted by the distance of the charge x from this interface. So that is 0, that is x, dx, integrated between 0 to the thickness of the dielectric d. Remember that integral? Anyway, once you inject charges, that adds to this rho of x. Depending on where those charges are, they'll impact this QI term, the flat band voltage, and therefore the threshold voltage, okay? As I have more and more negative charges trapped, the flat band goes up, the VT goes up, okay? And clearly that's bad from a circuit point of view, because then the transistor will not have as high of a drain current, your timing goes off, and at some point the chip will fail, okay? You'll also notice that the slope has reduced, okay? So the gain also goes down, and that's because you have more charge carrier scattering. The effective channel mobility also goes down, okay? So these are examples of hot electron damage. Now that I've moved from SiO2 to high K, you have to figure out for hafnium oxide, for example, what the delta EC and the delta EV is, plus the electron versus the hole mobility. So it turns out still hot electron problems in a transistor are more problematic than hot hole problems. All right. So that's one of the problems that's shown in this overview chart. Okay, so you get hot electron damage. Okay. You can also get other problems due to electrostatic problems, okay, which is called punch through or drain induced barrier lowering. What is that? Well, let's look at a transistor, a long channel device shown by this dotted blue line, and its corresponding band diagram shown by this dotted blue line. Okay, so that is my potential barrier between the source and the channel. And the way I turn the transistor on is apply a gate voltage to reduce that barrier below the onset of strong inversion, right? Now let's see, I disobey Dr. Denard and I scale down the channel length from this channel length to this channel length, roughly by what, a factor of maybe 3 in this case, okay? So that's L1, that's L2, so L1 is roughly 1/3. But I don't follow Mr. Denard's laws. I don't scale down the vertical dimensions, okay? So my junction depths are the same. I haven't changed the channel doping. My depletion region is the same. Everything else is the same. What's going to happen? Well, I draw the corresponding band diagram, okay? And I see what happens as a function of drain voltage, okay? So long channel shown by this dotted blue line, as I change my drain voltage, you know, this depletion region over here increases gradually, and it does this, and I go to lower and lower energies over here, right? But notice that will not change the potential barrier between the source and the channel. Therefore, that will not change the formation of this inversion region in the channel, okay? And the transistor will be well behaved. In other words, ID as a function of VD will saturate, okay, for different VGs. On the other hand, for short channel, notice what happens. Here, as I increase my drain voltage, these energies go down. And if you solve that two-dimensional Poisson equation, what you'll find is you'll end up lowering the potential energy barrier between the source to the channel, not because of the gate voltage, which is what you want, but with increasing drain bias, right? And that's why this effect is known as DIBBLE, or drain-induced barrier lowering. So the drain is lowering the barrier. What barrier? The barrier between the source and the channel. You'd want that barrier to be controlled only by the input gate terminal, but here the output drain terminal controls that. And as the drain voltage causes this barrier to reduce, electrons can be injected more easily, the current doesn't saturate, okay? So that's the reason. Okay, So that's what dibble is. In an extreme case, the drain current can go up so much where the depletion region of the drain kind of overlaps with the depletion region of the source, and that effect is called punch through. Okay, and the net upshot is the output impedance drops. Okay, the current keeps going up. Okay, so how do you think you'd solve this problem technologically? You can solve this by increasing the channel doping, because if we increase the channel doping, these depletion regions will shrink. Okay, and then this drain depletion region will not be able to control the source to channel potential barrier. Okay, so if you increase the channel doping, even for short channel behavior, the depletion region over here shrinks, and the drain will not be able to modulate the source to channel potential barrier. The other thing you can do is to apply a negative substrate bias, because if you apply a substrate bias, that increases this potential barrier, and this problem of dibble gets mitigated. Okay. Once I understand this, we can go back to this picture of advanced MOSFETs. Okay, so modern day MOSFETs have moved away from bulk MOSFETs that we've been discussing so far. And one geometry that's become very popular is a so-called Finfet, sometimes also known as a multi-gate MOSFET. Okay, the idea over here is as follows: you don't make the transistor on this bulk silicon substrate, but you etch a very, very narrow fin of silicon using plasma-based reactive ion etching. And then you have the gate wrapping around this channel from three sides. Notice here, the gate only controls the channel from this surface. But if I have a narrow fin and the gate wraps around it like an inverted U, the gate potential can control the channel potential here on the left-hand side as well as on the narrow top surface. Okay. And that's what you want, because you want the channel potential to be controlled by the gate, not by the drain voltage, which can then give rise to dibble. Now, can anyone tell me what the transistor length and width is for the Finfet? Well, the length is clearly that dimension, right? From the source to the drain. So that's the width of this gate electrode in this direction, right? But how about the width of the transistor? In a planar device, that was the width, right? But here the width is this vertical dimension of the fin plus the horizontal dimension, which is typically very, very thin, plus this vertical dimension. So it's twice the fin height. So the width is 2 times the fin height plus the fin width, right? Fin height, fin width plus fin height. Okay. The other advancement in current day MOSFETs is called strained silicon MOSFETs. Okay, and this is a little bit harder to understand. This is geared towards improving the channel mobility mu. Okay, because remember the drain current is proportional to the channel mobility. Okay, well, mobility, you may remember, is given by the charge of the electron times the collision time divided by the effective mass of the electrons, right? The conductivity effective mass. Now, I don't know if you remember, I mean, this is way, way back before spring break, but in the case of silicon, in the conduction band, we said that you actually have 6 energy equi-energy surfaces. Okay, these are these cigar-shaped energy ellipsoids, okay, near the X point in the conduction band, in the Brillouin zone, okay, where you have a high longitudinal effective mass and a lower value of transverse effective mass, okay. It turns out in bulk silicon, you have 6 of these energy ellipsoids. They're all equally occupied. But in a MOSFET, only because of details of the electrostatics, only some of them are occupied. And then what you can do is, by applying mechanical strain to the crystal, you can break the symmetry of the cubic crystal. And basically, you can have only these values with the lower transverse effective mass contribute to the transport. This is very complicated. You know, clearly that wasn't a good enough explanation. The punchline is, by introducing mechanical strain on purpose to these MOSFETs, you can reduce the effective mass of the carriers. That raises the mobility of the carriers in the channel, and that's how you get higher currents in a transistor. In case you think that this is all exotic physics, all modern companies like Intel and Samsung and all these companies use this sort of a technology as well as Finfet type technology, and that's what you have in your laptops or cell phones and things like that. So this is all very, very real application of quantum mechanics and quantum physics to transistors. Okay. Any questions? All right, I guess we're out of time. So we'll wrap up short channel behavior of MOSFETs in the next class and then jump into BJTs. All right. Any questions? All right. See you next week.